So that's kind of the challenge to most plumbing designers, is the fact that, well, they've been comfortable with 25 or 50 feet, but now, as we'll talk about, the energy code says no, no, it has to be 2 feet, and so that's the interesting thing about this. So we'll go into some detail about that. The problem with a 25 feet or 50-foot, single leg connection, non-circulating pipe, is the hot water is too far away from the fixture. So, and there's problems with that. Certainly, the hot water cools down through non-use of the fixture. So, if that fixture is not being used, well, that water sits there. At one time, it was hot as the fixture was used and drawing the hot water from the source to the actual connection point and to the fixture. But if that fixture is not being used, and we know there are many fixtures out there that don't be used, especially in a healthcare environment such as showers, etc. But not all fixtures are used all the time. So that water is was once heated up, and then it cools down, and now it takes some time to get to that fixture, etc. Um, and so as that water sits there too, so typically it's going to fall into a temperature during non-use, that stagnation can grow. And so you have issues of Legionella and other bacteria and biofilm growth due to that stagnant pipe. So this IECC code really covers a lot of things, not only energy savings, but some of these other non-intended results coming from this IECC code, and one of them being bacteria and biofilm growth. The other problem is that the public laboratory fixture flow rates are so low that you'll never get hot water if that thing's 25, 15 feet away. It's just, it's difficult enough, even if we've brought it down to 2 feet. It's still, as these fixture flow rates get, smaller and smaller and lower, the water's not on long enough to really draw that hot water from the source to the actual the use point. And of course, the infrared fixtures, they're on, they're off, they're on, they're off. It's not a constant flow, so that doesn't help anything. So really what we want to do is bring that hot water source up in the ceiling normally, bring it down to that fixture connection point as close as we want. So what the results of this existing situation is the long pipe lengths that are non-circulating lead to poor hygiene, because nobody wants to wash their hands necessarily in cold water. It leads to user discomfort, wasted water because we've heated it up. Now it's cooled down, we're having to waste it down the drain. Wasted energy comes along with that, and increased water costs for the building owner. The solution, as mentioned, is the IECC code, as we'll talk about. And that's bringing the heated water source down closer to that fixture. So one of the big problems, if it's 25 foot away, you can imagine if it's 50 feet away, that it takes about 63 seconds with a half a GPM fixture to clean out that 25 feet, given a 1/2 inch copper pipe. So if that has cooled down entirely because the fixture wasn't used for an hour or so, then it's going to take 60 seconds for that water to get there. And if I were to not say anything for 60 seconds, that's going to be a long time. 2 seconds will drive you crazy. But so if we bring that down to 2 feet now, that with that fixture flow rate of a half a GPM, it's going to take just over 3 seconds, and that's more acceptable, obviously, because nobody wants to wait around. And you just can imagine the amount of water that's wasted waiting around for that, and the energy that it took to heat that water up. So that's part of the big problem here, and the solution to having to wait and wait and wait. The other side of it is the amount of the water that is in a 1/2 inch copper pipe that's 25 feet long is generally about 6 gallons, just over six, or excuse me, a quarter of a gallon, just over a quarter of a gallon. So if you take, okay, we got 25 fixtures on this one floor, then that's 6 gallons that sits there and potentially has been heated up and now has been cooled down. And oh, by the way, to get that hot water, we have to drain it and just throw it down the drain, and it's going to take 63 seconds to do that. So by bringing that non-circulating pipe length down to 2 feet, Okay, now we only have 0.02 of a gallon in that length of non-circulating pipe. Okay, with 25 fixtures on the floor. That's only a half a gallon compared to 6 gallons, and that's just 25 fixtures. That's just maybe one floor of a hospital or what have you. You multiply that by multiple floors, multiple buildings, multiple cities, states around the world. You just can't imagine the amount of wasted water and wasted energy that is happening. So, as mentioned, well, there's really two codes. The IECC Energy Code was first appeared on the books in 2015, and to the plumbing industry, very little known. Even now, it's been in the books for up until now, so it's been in the books for 6 or 7 years, and there's still a disconnect between the plumbing industry and the energy side of it. So um, because it's not in the plumbing book, okay, we're plumbers, that's an energy thing. So they don't realize that no, there is these things come together, and it is a code that needs to be complied with. And so part of the problem on the plumbing side, plumbing design side, contractors potentially, first of all, they're not necessarily familiar with the code. Even today, I can call on some engineers and contractors, and they're just not familiar with it. And if they are familiar, they're not sure really how to comply with it. How do you so easily just take a 50-foot connection and reduce that all of a sudden by code to 2 feet? So
Hey, Craig.
yeah,
Craig. Hey, this is Rich. There's a question in the chat
yeah,
about, is the 24 inches from the stop valve under the lavatory, or do we count the flexible supplies? So it's from George, and I assume he's asking where we stop the developed length from the hot water source.
that's a good
Um,
question. Yeah. And that always comes up, and I'll show that in a second in a slide or two, but it is from the fixture connection point. So it is actually from the fixture, does not count that flexible hose. And I'll
Thank
show
you.
that in a graphic here in a second. Thanks for that question. I don't see those questions, so at any time, please go ahead and throw them out.
Yes, sir. I'm monitoring the chat, so
Okay,
I'll let you know.
great. Getting back to this, so it is difficult to comply, and it's easier not to, especially if the code is not being enforced. And I go around the country, and I'm in these situations, talking to contractors, talking to engineers. Some states it's enforced, very, very strictly. Other states it's not at all. So the plumbing, side of it as well. If it's not being enforced, I'll just, I'll try my luck and I'll go with it until something happens. And honestly, that's what happens. And so that's really the purpose of this seminar, this webinar, is to help people understand that there is a code out there and it does need to be enforced. This is the reason we have these codes, and we just kind of went over that. The energy savings and the water savings, et cetera, et cetera. So in some cases, it's looked at as, well, there's no reason to comply. I'll do it when I have to. So one of the wonderful things that is going to happen shortly in the 2024 IPC plumbing code book is to bring those two codes together. So there will be an entry and a provision in the IPC plumbing code book that will state um, in occupancies that are required to comply with the commercial provisions of the IECC Energy Code, you're going to have to refer to that code. So this will be an entry in the plumbing code book. So this has never been done before, and so there's never been a pointer to tell the plumbing designer, hey, there's an energy code out here that you have to comply with. So this is going to bring that connection closer to both the plumbing and the energy code. And so that makes a lot of sense. We're kind of happy to see that now. So here is actually the code. So if you go to the page on the energy code book, you will see this, and this is pretty much the entire code here as it reads. And so this is hard to read, and you don't have to read it all, but the difficulty is the code refers to public lavatories and refers to other fixtures relative to how long the non-circulating pipe length can be. The challenge is the public lavatories. So we're just going to talk about that. So the code deals with public lavatory faucets. That's what we're challenged with. And the uh, the the whole purpose is to reduce the non-circulating pipe lengths, and that can be done in two ways. So you can reduce that non-circulating pipe length by uh, just the pipe length method. How long is that pipe based on the diameter of it? Or you can reduce that pipe length by volume. How much water is in that pipe? And so typically what we see, we rarely ever see anybody making the calculation to figure out the volume, because what we generally see is it's certainly easier to just look at the pipe length, and it's either 2 feet or it's 3 feet or whatever it is, and that's a heck of a lot easier than trying to go through any calculations. And in addition, the calculations for pipe volume method uh, typically equate to the actual length of pipe anyway. So there's hardly any reason to really to go through the calculations of that pipe volume method. So here's the diagram I was going to get to, Richard. So if we look at this energy code, they're talking about maximum allowable pipe length. And so the maximum allowable pipe length from the near source of heated water to the termination of the fixture. So the fixture terminates right here. And so the near source of hot water is generally in the ceiling. So what this code is saying, well, you have to bring that hot water source, which is up here in the ceiling, down to within 24 inches or 1.5 ounces per volume of the fixture connection, which is right there. And so that is what the designers are challenged with, and that is what code officials will have to look for to enforce this code. As far as near source of heated water goes, included in this code is the description uh, of those heated water sources, and it's water heaters, circulating water systems, heat trace temperature maintenance systems. Those are the heated water sources that are accepted relative to this code. Here's the actual the table that you had seen. This reflects the actual pipe length if we're dealing with just the pipe length. So if you have the nominal size of your pipe coming down from the heated water source in the ceiling here, if that is a 1/2 inch, then you look over here to the public lavatory faucet, there has to be a maximum of 2 feet of non-circulating pipe length. And you can see it plain and simple. The hot water has to come down here. That hot water is either a water heater, circulating water system, or heat trace system, has to come to within 24 inches of that fixture stop. If we look at
Hey,
the,
Craig,
yeah,
can I just point out something on the chart real quick? If we notice that there's also the second column for other fixtures and appliances. So say you had a commercial
yeah,
3 comp sink being fed with a 1/2 inch pipe, you would still be limited to only 43 foot, which is more restrictive than the model IPC of 50 foot. So it's not just public lavatory faucets we're talking about all other fixtures and appliances as well. Correct, Greg?
that is very true. I think the common practice, what we see, Richard, is most of the designs are bringing those connections closer to this 50-foot anyway. So I think it
Mhm.
would be rare to see a 50-foot non-circulating pipe length, and that's giving credit to best practices. But you are
Mhm.
right. If they're not, then 43 feet, uh, would be the allowable non-circulating pipe length if it's not a public laboratory. So that's a good point. But generally, the challenge is these public laboratories. That's the one that the compliance isn't quite there, and that's the one that officers, compliance officers, will have to look at, enforcers. So we talked about the maximum allowable pipe volume, which is 2 ounces for a public faucet. Again, not more than 2 ounces, and so that becomes, generally speaking, about the same as the linear length of the pipe itself. So what we see out there is, and if you're a code enforcing official and you look at it, it's going to be a lot easier to say, okay, it's more than 2 feet. Then you can do the calculation or have somebody do that calculation. But if it's 2 feet, generally it's going to be fine. Certainly if it's coming from a 1/2-inch supply pipe. Public and private laboratories. So this is the definition in the IPC code book, November 2018. And so the public fixtures include general toilet rooms. You can read this: schools, gymnasium, hotels, anywhere really where the laboratory can be accessed publicly. So somebody can just walk down a hallway and duck into to use a public or use a fixture. That that really kind of makes sense. If it's a private fixture, then it's really designed for use for a specific individual or a family, but it's out of the way. It's not something that you can just kind of walk by and see. You would have to kind of open a door. You'd have to go into a room. So I don't think we have a lot of difficulty, identifying these two differences in classification, but there they are. So typically a public laboratory is something that is accessed by anybody in the public. So you'll see all these in the airports, the gymnasiums, every school. They have tons of public laboratories because they are all pretty much accessible. So that's something that helps to identify which laboratories are public and which are not. This is the latest adoption map for energy code, IECC energy code throughout the country. And so this is not specifically that one code, but this is the energy code in general. And so we do see areas of enforcement that are much greater than others. Certainly, one of the biggest enforcement areas is Texas, and Florida, of course, is totally bought into this, and these codes are being enforced pretty stringently. There are some areas of the country not so much, but hopefully this seminar will help. One really interesting thing here that has come to my attention in the last couple months really is that the state of Wisconsin has taken this IECC code further, to their own credit, and they've stated that it's not just a public laboratory. So in the state of Wisconsin, it's almost certainly every sink where hand washing is expected. So they do list all these other fixture types: exam rooms, sinks, shared public toilet rooms, of course, and then private patient rooms, even unless there's an additional laboratory outside. So this is even making it more strict, and not just for public laboratories, but really almost every fixture that's accessed not only publicly, but where the use of the sink for hand washing is expected.
Craig, we have another question in the chat that I can see right here. It's asking if a single occupancy restroom, private or public, if it's in a classroom and serves a specific group of people, can you walk into a school without a badge or escort schools in my area? I'm not following the whole question, but we need to look at what the definition of public and private is within the plumbing code to determine if it's a public lavatory or a private lavatory. And I hope that answers your question.
Yeah, that IPC code book will point that out, just as I showed on the screen there, identifying what is considered public and what is considered private. I can go back to that, and that's the description that you'll find in the IPC code book.
So the other question in it that supports that, and they're specifically asking, how does ICC define private restrooms in an office private suite? So while you, Chris, or Craig are continuing, what I'll do is I'll copy that definition from the code and post it in the chat so everybody's aware. Okay?
Okay. Yeah. Super. Great.
All right.
Okay. Thank you.
Yep.
Okay. So let's talk about the challenges that we see and the reasons for non-compliance, and what the designer looks at. Most designers are kind of rolling their eyes, going, "Oh boy, is this really necessary?" Because they don't have too many options, and so this is one option of bringing that hot water source from the ceiling generally is where it is down to within, say, 2 feet. And we say that because most of what we see is the half-inch piping coming from that heated water source to the connection fixture. So, it's just a kind of a standard. If it's a half-inch pipe leading to that fixture, then it's 2 feet or 24 inches. So that's kind of a nomenclature that just spills off the tip of the tongue. So how do we do that? There's one way, and one way is to take your supply pipe, which runs in the ceiling, and have your T-piece connection drop into the room through the wall, and make your connection, and then back up to the supply pipe again, and on it goes. Typically, you'll see a full stop, always closed stop valve there, and that allows for the water to move into the room and connect to that fixture. This becomes very challenging if you have a 2-inch supply pipe. Not so much of a challenge if you're dealing with a half-inch or 3/4 inch or maybe even a 1-inch. But with 2 inches of supply pipe, you have 2 inches of insulation, and to get that assembly down through a 4-inch wall becomes very challenging. But this is probably the easiest. Even a layman would think, well, if asked the question, how would you do that? I'd do it this way. But not necessarily the best way, but it is a way to comply, and you might see this in the field. It's difficult to route that piping, and it's very expensive. So you're really looking at $20 a foot, and that can become a challenge. I get you in a half hour or so. I'm right in the middle of a presentation here, or you might have to come back. Or, excuse me, yeah, I have to, yeah. Sorry, I had a deliver here just at the front door. But in any case, I'm going to continue with this. So yeah, so that's a difficult thing. $20 a foot for a 2-inch copper pipe. That adds up. If you have, say, 50 feet, that's $1,000 of 2-inch piping plus installation that you're trying to get through a 4-inch wall. And then your shut off is how do you shut this? How do you shut this off? Of course, you can have stops here. This in a full stop position all the time creates stagnant piping and creates bacteria growth. As soon as you unleash that, then there's some potential issues with that, obviously, as well. This is another method. This is the more traditional method. This kind of makes more sense, I think. It just depends on the designer, depends possibly on the building layout as well. But typically, we'll have our 2-inch supply pipe. We will have a T-piece dropping into the room, connecting to the fixture, and then becoming a return. That return pipe goes up to a return pipe running in parallel with the hot and cold in the ceiling. So that's bringing the supply, and this goes through a balancing valve. So the only way to get the flow that is required with multiple rooms, for instance, or to get the flow rate coming into this room at all, is to have a balancing valve there as well. So we've got more connections, more points of failure. You have a balancing valve that needs to be adjusted from time to time. And so this is another way to do it, possibly a more common way to do it. But really there's just a couple ways to do that. And that's another one. A third
Craig,
way, yeah.
Craig, one other question just came up in the chat. If the main line is 2-inch, for example, can they just bring a half-inch line, a half-inch, and let the main line up?
Yes.
I assume.
Yeah.
Yes.
That is absolutely yeah. So that's normal. That's normally what is done. So you have your 2-inch supply pipe in the ceiling, and you branch down to the fixture, which whatever diameter piping that the fixture requirement is calling for, whether it's a half-inch or 3/4 inch, or maybe you have multiple fixtures that requires a 3/4 inch. But that's exactly what you would do, would be to reduce from the supply down to a smaller diameter to the actual connection there. So moving on, here's so this is the new technology here that has come into the U.S. here in the last few years here, It's called a Venturi flow splitter, and so it's a single valve, and it really kind of it eliminates the need for return piping in the ceiling, and there is no balancing valve required. So it allows you to place the flow splitter valve on the supply pipe, and I'll show this to you. And as long as there's water moving through the main supply, then there's an insert inside of this flow splitter valve that diverts some of the water that would normally go through it, a very small percentage of the water that would actually constantly circulate into a connected loop down to the fixture. So that allows for constant movement of the water without the need for a balancing valve and without the need for return piping that you'd normally have to have in the ceiling. And so when we talk about the requirement for bringing large pipe sizes into the wall space, this was a designer in Dallas that said that they do that. They do that with a 2-inch pipe, and that's their method of complying with that IECC code. And so they've been asking their architect for 6-inch walls because they're bringing a 2-inch pipe with 2 inches of insulation, 4 inches through a 4-inch wall, just not working. So they've gone to the extent of probably begging their architect for 4-inch wall, or excuse me, 6-inch walls, and that's really probably going too far. I know architects are not happy about giving up space, and that's something that really this is how challenged they are by this code. The flow splitter technology almost seems like it was designed for this IECC code. It was really designed to keep water moving into a room, into a bank of fixtures, to avoid stagnant, non-circulating pipe lengths. So it's used for an effective solution for complying with this energy code, and for providing hot water at the fixtures immediately. That's the whole real purpose of getting this heated hot water source down from the ceiling to the fixture. And then in the end, it saves water, saves energy, and of course, throughout the entire design process, there will be some pipe savings. And one other thing, as long as you have water moving, so you have water moving from the main supply down to that fixture, you're actually increasing your residual counts of the either secondary treatment of chlorine or chemicals into the system, or just helping to maintain residuals that come in from municipal supply. And so any stagnation of that water will tend to dissipate the chemicals that has been provided in the water. So this is the concept of the flow splitter, and the flow splitter concept, or the Venturi concept, was introduced 250 years ago. And so this is the Giovanni Venturi concept, where he had a pipe. Back in the day, it was called a vessel, and there was a restriction along the way of the fluid flowing through that vessel. That restriction creates a pressure difference. The pressure difference will cause movement into a parallel path, which is a connected loop. And so 250 years later, this is the Kemper flow splitter technology. It's virtually identical. The difference is that instead of a fixed orifice, Kemper has provided a dynamic moving insert that helps this Venturi concept work in all flow conditions. And so what I might do here is share my video. First, I'll look at this. This is what the inside of the Venturi flow splitter looks like. This is a dynamic insert, and so what I'll do here is share my camera if I can. Not sure
If you stop sharing your screen and then turn your camera on, everybody should be able to see you, Craig. And then maybe there was a question in the chat about a pressure a balancing valve being under like a rough-in test or a final pressure test. Maybe you can explain how those concepts work with the flow splitter. So, 50 pounds of air or working water pressure, is that typically what you're seeing on these?
Actually, I'm not. You're talking about on the on which on the
So
mounted.
once it's installed in the field, and the inspector shows up to do the pressure test required
Yeah.
at the rough in stage, uh, these no issue with, if it's other than a plastic piping system to put 50 psi of air on it, or just to simply pressurize it with working water pressure, correct?
Yes, yeah. In fact, are we talking about this flow splitter product by itself? I know
Yes,
this
sir.
component, yeah, it's 290 plus pounds psi. Yeah, so certainly will endure anything you will find in a normal potable water installation. Yeah,
And then somebody asked, is there a pressure drop table for this fitting so that when they install it, they can add that into their calculations? Craig, do you guys have that data for people?
absolutely. Yeah, that is on our website. Yeah, you'll
Okay.
find the charts on our website for different sizes.
And will you, just when you get a chance, put the website in the chat for us so people have that link, Craig?
Okay, I can do that.
Excellent.
That website, it might be easier if I just were to say it, and maybe Richard, you could provide this or pass
I
it.
will.
It's kemperwatercontrol.com.
I will put it in the chat, sir.
Okay, I'm just looking here at the share button, share content. Okay, share the camera, I guess. So I'm thinking you can probably see me,
Yes, we can.
sadly enough. So this is the picture that you had seen. Let me just move this over here. This is the picture that you had seen on the screen. This is the cutout version of the Kemper flow splitter device. And so this is actually placed on the primary hot water supply. So there are 6 different sizes. This is our largest. That's a 2-inch diameter, and it goes down to a 1/2 inch. So this again will appear right on the supply pipe, your hot water supply pipe. And then there are connections that drop down into the room through the wall and connect to the fixtures. So as was mentioned earlier, these can be a 1/2 inch, 5/8 or whatever the connection needs to be. But with this insert, the way this works is when there's water moving through this flow splitter in this direction, of course. So as water is being demanded downstream, so water will move in this direction. If there's full demand, peak demand happening at that time, then this will open fully, and that'll allow uh, about 98% of the water to go directly through the main portion of that pipe. But the resistance and the pressure difference will always drive water into the connected loop. So although most of the water is going in this direction, you will have a constant exchange of a percentage of that water dropping into the room connecting to the fixture. And so that's the concept and how it works. If there's very little demand, then a larger percent of the water will probably go through through the connected loop. But again, full demand, you can see there that opening up, allowing for most of the water to go right through the main portion of that pipe. So let me get back here and share the screen. I think this is what we were looking at here. Bear with me 1 second. There we go. So that's what you had just seen there. And this is the way it looks. So this is the perfect example of a public laboratory, and there's only one in this, or it just happens to be a public laboratory that's out of the way, for instance, or there's just one of them. And so maybe it's in a lobby of a building, and there's an elevator, and happens to be a public laboratory there. So if you do have that circulating, there's your hot water source in the ceiling, there's the flow splitter. As long as there's water moving, and typically we do have water moving. Obviously, we have fixture usage during the day, and we have recirculating pumps on at night that will move water when there is no fixture usage. But as long as there's moving water through this flow splitter, then we get a constant exchange of water into that room, right down to the say the 24-inch connection point. And so this can be done for multiple fixtures, or it can be done for just a single fixture, and that's pretty much the IECC code in a nutshell right here, if you're looking at how to comply. So a loop is connected down and back to itself again within the 24 inches of that connected fixture. actually an interesting one here. This is not far from where I live in Naples, Florida, and so we have the main supply pipe moving in this direction, and it's looping back, and so that's our return pipe looping back, and so as the main supply is moving through, it actually moves through a flow splitter here. This flow splitter is looped down to within the 24 inches here of the connection, and then back up to itself again. And as the water continues to circulate on the main, here's another one here. So this loop comes out here, it comes down, connects to within the 24 inches or 2 feet because it's a half-inch pipe dropping down there, and then back up to itself again, and then on to the resort. So that's typically exactly what you will see on a plan if you're looking at the use of the flow splitters to comply with the code. What I actually saw when I went out there was the fact that the hot water is actually being moved through the flow splitter, but the flow splitter connection came out here, and instead of looping down like it's designed, the contractor actually connected it here and back to itself again. And so the loop is off of the flow splitter, okay, but the loop doesn't go down. They just had a single connection. It was probably 20 feet or more, 25 feet, that went down to this public lavatory. So they installed it wrong, or I'm not sure why they did it this way, but this is the way it should have been. So it should have come this way down, connected down here, not up here, and then back to itself again. And so the other part of this building was already buttoned up and sewed up, and I'm imagining they probably did the exact same thing.
Hey, Craig, I got two questions in the chat from Antonio. The first one is, do you as the manufacturer provide data for pressure loss as determined flow rates through the Venturi loop as well?
It's a parallel path, so it would be the same as the pressure loss through the main. We do have a calculation tool that does exactly that. So that is a link that we can provide. It's on the UK website. It's not on the US website right now, but it does allow you to choose different flow rates through the primary part of that Venturi valve, and then it gives you the flow rates that would occur through the loop. So if you decided I have a 2-inch Venturi flow splitter, I have 40 GPMs going through it, what would be the velocity of water going through my connected loop, and it'll actually tell you that velocity.
And Antonio's second question was, is there a maximum developed length for the Venturi loop?
That's a great question, and it really depends on the expected temperature loss. So, if you have multiple loops, or excuse me, multiple Venturi flow splitters in series, then you will have multiple mini loops, basically. So, the longer these loops are, the potential for losing temperature in those loops as water moves slowly through the connected loop. So generally speaking, we've seen them with over 100 feet, but as soon as you put maybe 15 or 20 of these in series, those connected loops should be shorter, because you might lose more temperature than your delta T will allow for. So it really depends how many that you have in series.
We have a couple more questions, and I know we're running low on time because of our
Yep.
IT issues at the beginning. But
Sure.
do you guys have a cost analysis showing energy water savings versus the cost of a valve? And the second part of that question that's kind of in the same realm from Dave is, what's the payback? Like, how long is this as opposed to looping all the way down and back up and doing everything? You guys have some of those cost analysis available?
We really don't. I mean, we have, generally speaking, it's, the savings through piping is about 15%. And then you have savings through, the reduction of piping in energy. But typically, it's a 50. We don't do it because it's very difficult, based on so many different building configurations. There's no one calculation that meets them all, and we just don't have that information. So it really had to be done on a single building project. But we generally will say 15% because we have seen that. In fact, I have an example on this presentation that shows it really just shows the savings, the pipe savings, and that pipe savings, the reduction of pipe savings reduces the energy costs. And so we were seeing pipe savings and energy savings of about 15% minimum.
Thanks, Craig. And I think really this next question might be more for Chris. Chris, can you see the question in the chat about the recirculating system and the hot water demand? It's kind of long, so if you want me to read it, I can.
I'm kind of looking back through the chat.
It's the last one that was just posted.
I see what is the payback? That's
Then we see.
okay, here we go.
Do you see the requirement? Yes.
Demand control pump.
From Chuck.
According to demand for hot water. All right, so the question is in regards to the recirculation pump and when it actually runs. We see a conflict in minimizing the hot water.
Yeah, I think generally the pumps will turn on when there's no usage in the system.
Yeah, typically there's something to activate the pump.
Right.
But again, I would think just limiting the amount of water within that, between the source and the fixture itself would probably provide some benefits, but I don't have any sort of analysis to show that. So at the moment, there's nothing that's come up in the co-development process that's address that accordingly. But that's not to say that there might not be some issue there.
Yeah, I believe maybe what the is being referred to is the requirement that when the hot water is not being used, we have a timer for times when the building's not occupied, and then we have that temperature sensing device that once the loop is up to the required temperature, we shut the pump off. But as that temperature comes back down, Chris, right, then the pumps come back on to make sure that that loop stays at the desired temperature. Correct?
Mm-hmm, mm-hmm. Correct.
Chuck, I hope that addressed your question. And then, right. And then we've got, assuming you're using local sensors like an occupant load sensor and you're using local area sensors. So those are demand recirculation systems that only come on when there's occupants in there, correct?
Yeah, I'm not familiar with those for a master research system.
And David put a note in about OSHA, but I'm not too sure. Requires continuous operation of the pump in healthcare applications. I'll have to. I'm unaware of that OSHA requirement. Chris, I don't know if you've ever heard that one.
No, I'm not familiar with the OSHA requirement.
Yeah, that makes sense because you're constantly moving the water, so constantly maintaining that temperature, even though there's no fixture usage.
Okay.
Okay, so I'll just continue here. This is, if you're looking for the flow splitter in buildings where compliance is required, this is what it looks like staring up at the ceiling here. So this is like a 1-inch flow splitter connected to the primary supply pipe here, and then this is the connection down into the room. Generally speaking, with stop valves to cut off that room completely for servicing. Here's another view of it with press connections. And this is it actually comes with a clamshell insulation jacket, so if it's fully installed, this is what you'll see as opposed to this here. This is what it looks like relative to other installation wraps. So it's very neat, very tidy. And here's the loop coming down in between the 4-inch wall and going back up again with the connection to the fixture within 24 inches. So this is typically how we see that being done. And this is some of the cost savings. So if you're looking at the use of the flow splitter compared to the traditional way with the bouncing valve and the return pipe in the ceiling, that's typically what we see. And so this is the perfect scenario where you would have the hot water source, water going in a loop fashion, the primary supply pipe, and then flow splitters off of loop. In this situation, we have at least 15 of these. So this is where you may lose a little temperature along the way through each of these, and that would justify, well, how many can I have on a single master loop? In some cases, you may want to split this master loop into two, but this gives you circulation into every single room to each fixture. And what you've noticed here is there no supply, or excuse me, no return pipe traveling in parallel with this supply. The return pipe is after the last flow splitter installation back to the heated source or the water heater. This is the return pipe that is saved in this specific application. Typically, this would run in parallel, and then if you wanted to circulate down to that fixture, you would have all of these balancing valves that would be required. So there's tremendous costs there in piping and callbacks and balancing each one of these rooms. So,
Craig,
yeah.
do you, new question, do you have a CAD detail that can be used?
We do, yes. You'll find those on our website, that website that I had given you, Richard.
Yep. And I put the link in the chat. So that should answer that one. Thank you.
Yeah.
I know we're running short on time and we're a little over. So
yeah, I can race through these here and see if any are duplications.
I don't mind sticking around for a few extra minutes. I understand some of the attendees may have other meetings to go to, and I just want to let everybody know we're going to just kind of move forward with finishing this, even though we're going to run a little over, and we're going to provide everybody with a PDF version of this PowerPoint, as well as a recording link to this once we get the attendance report from WebEx. So Craig, just take your time and do what you got to do.
Okay, very good. I'll thank everybody for attending. For those who have to cut out, thanks for hanging in there through some of our challenges at the beginning. This goes back to this is a miniature version of what I had shown you, where it makes sense in this particular application. So the heated water, the hot water here, the source of the hot water in the ceiling, doing a loop, and then flow splitters getting to these public laboratories. So these are the public labs that need to be complied with relative to that 404.5.1. And so the flow splitters used to obviously get down to that connection point, looping down, etc. So this is a pure IECC code application here if you're looking at drawings. And this is kind of.
Hey, Craig, I just had something that popped into my head as a question that may be lingering in everybody. A lot of your diagrams show the flow splitter being used for one single lavatory location, right? Do the flow rates and pressure drop through your valve allow for more than one lavatory? So if I have a bank of 3 or 4, can we do that with one flow splitter, or do you need one per lavatory?
No, that's no problem whatsoever. It really has nothing to do with the flow splitter because you're drawing water from the primary pipe. So you'd really size your loop pipe based on the number of fixtures and the demand, the fixture demand of those fixtures. And so it's you would be pulling whether your connection is a 1-inch down to those fixtures, a 3/4 or a 1/2 inch. When that fixture is turned on, obviously creates a leak in the system, and that draws water from the primary pipe. In fact, it actually drives water or draws water from both sides of the flow splitter. So you're not only pulling water from the left side, for instance, if you're looking at it, You actually pull flow from both sides, but yeah, there's no pressure drop associated really with in that loop.
Thank you.
You're welcome. This is an interesting application where you have the three pipe configuration of cold, hot, and return. Yet there are public laboratories that need to be connected to within the 24-inch or so specification. So what they've done to save return piping is to come off the supply in a kind of a master mini loop through a balancing valve back to the existing return. But in doing this, they're able to use flow splitters in these 4 spots here, able to connect, yet they don't need the balancing valves that would normally be required. And also we're eliminating a return pipe that also would have to travel in parallel with this loop. So this is a neat hybrid application that we're seeing more and more of as well. And then very simply, if somebody comes to us and they say, here, we have this project, how do we do this otherwise? How do we save piping, et cetera? How do we utilize the flow splitter? And this is one we just showed you, where you have your typical cold water, hot water in return in parallel in the ceiling. You're running off with the hot water connecting and then back to the return again. And to do this same thing, circulate to these public laboratories, we would eliminate all of the return piping altogether, eliminate all the bouncing valves, and place in the flow splitters, and reduce the return piping just to this back last portion there. So that's kind of a basic look, and this is a real project from Oregon that came to us, and one that makes a lot of sense and provides some cost savings, and allows you to comply with that code. And then just finally, looking at another benefit of circulating water is looking at this as a young kid. We were always told, hey, don't drink from standing water. If you can and you have to, drink from moving water, drink from the creek. Do not drink from from the lake that you see here on the right side. And so I look at water systems the same way. And if you're looking at healthcare applications, especially, you want to move that water. You want to keep it moving to avoid that stagnant growth of biofilm and bacteria. So the single feed pipe can produce this effect if that fixture is not being used. And that's where the benefit comes in of moving water close to the fixture. And then finally here, this is looking at this is one of the cost saving questions we had. If you look at this 2-story, 4-room miniature building here with the the heated water here coming up and circulating in the ceiling, this is a traditional method using the return pipe in the ceiling and balancing valves in every room. And you can look at the use of the flow splitter, and you can almost look at that immediately and go, okay, well, there's a lot more going on the left, and there's certainly a lot more balancing valves. There's more piping. Of course, you do have the cost of the flow splitters, but the savings in this exact replica is 118 feet of pipe, and along with that comes about 250 watts of energy savings as well. So that's kind of the that's the perfect scenario where it does make sense. So that's all I have. I really appreciate the opportunity to share some of this knowledge with everybody that has attended. Chris and Richard, thank you very much for allowing me to present and for co-hosting. And you can see there that I have some contact information. You're all welcome to contact me directly through these numbers and email addresses.
Craig, one question just came up also. The product is noted as maintenance free, but with moving pieces, what is the warranty and expected service life of your flow splitter?
That's another good question. And the expected service life is 50 years for this product. It is deemed as a non-serviceable item. No need for access, no need for maintenance, no replaceable parts. And the expected and estimated service life is 50 years. So it is a building life product.
Great, thank you. I've already received a couple emails, and I just want to reiterate the fact that I'll be sending out a link to the video as well as a PDF version of this presentation to everybody who has attended and those that just registered as well, because I know we had a little bit of issues with the registration. So everybody will be getting all of the information within the next few days. So if there are no more questions, I'd like to thank everybody for attending, especially a huge thank to Craig with Kempler Water Control Systems for being willing to come out with us today and present this to all of our stakeholders. And Chris, huge thank you to you too and all you do for those ICC serves, right, on the energy code side.
Very good. Thank you, everybody.